92 elements are found naturally in the universe, and yet chemists have identified more than 12 million different and unique substances. How can this be possible? The secret lies in how elements bond together into compounds. When chemists unraveled the mysteries of compounds and reactions, they were able to explain the fundamental nature of matter. This remarkable achievement lies at the very heart of modern chemistry. There are only 3 different types of changes in matter: nuclear, physical, and chemical changes. Nuclear changes are those that occur in the nucleus of atoms. Fusion occurs in the sun and stars when 2 hydrogen nuclei fuse together to become helium. In the process, enormous amounts of energy are released, which travels to us in the form of electromagnetic radiation, or light. Fission is a different type of nuclear process, created in nuclear bombs or nuclear power plants. In this process, the nuclei of uranium atoms are broken apart and release energy. Radioactive decay is another form of nuclear change. In this process, the original nucleus of an atom decomposes to form a new nucleus, releasing radiation in the process. But although nuclear changes are vital in the universe, we tend not to be aware of them in our everyday life. Physical changes in matter occur when a substance undergoes change but retains its chemical composition. Water can be in the form of a liquid, a solid, ice, or a gas, water vapor, but it always has the same chemical composition, H2O. Another term for this is changes of state. Chemical changes are significantly different, and when they occur, there is an actual change in the chemical composition of the substances. The original atoms are preserved, but they combine in such a way that a new substance is created with a different chemical composition than the original. There are many examples of this. Metals can be melted together and form new alloys with a different chemical composition than the original. Plastics are made by combining different types of elements. In the process, new substances with unique qualities are created. Chemists make a distinction between pure substances and mixtures. In a mixture, different substances are mixed together but do not bond. Muddy water is a good example. The mud and the water do not join together, and if left to stand for a time, the mud will settle to the bottom. In a compound, however, the valence electrons of elements are lost, gained, or shared between the different atoms to create substances with unique chemical properties. These unions are called chemical bonds. There are 2 basic kinds of bonds: ionic bonds and covalent bonds. A neutral atom is made up of an equal number of positively charged protons and negatively charged electrons. Protons in the nucleus of atoms rarely become free, but electrons have the ability to move, and it is the valence electrons, those electrons in the outer energy level, that move and give the element its chemical characteristics. When an atom loses an electron, or more than one electron, it becomes a positive ion, because it now has more positively charged protons than electrons. If an atom gains electrons, giving it more electrons than protons, it becomes a negatively charged ion. These ions then attract each other because of their opposite charges. The 2 elements do not merge, they lose or gain electrons. The periodic table predicts when this type of bond is likely to happen. Chlorine is in group 17, and all elements in this group need 1 more electron to fill their valence energy level. All elements in this group strongly attract electrons. They are said to be electronegative. Sodium is in group 1, and all elements in this group have only one electron in their valence energy level. These elements are electropositive, meaning that they are more likely to lose electrons. Sodium is an element with only one valence electron in its outer energy level. Chlorine is an element with one electron missing to complete its outer energy level and become stable. When these two elements come close together, there is a natural tendency for the lone valence electron of sodium to move to complete the valence energy level of chlorine. In the process, the two atoms become ions and form an ionic bond. As a result, each of the elements becomes more stable. The new compound formed is sodium chloride, a substance everyone knows as table salt. This relationship is common in chemistry and has given rise to the octet rule, which states that atoms tend to gain, lose, or share electrons in order to acquire a full set of valence electrons. When ions are close together, they assemble into a pattern. Negative and positive electrical charges attract each other. For example, in sodium chloride, or table salt, the sodium ions are surrounded by the chloride ions, which in turn are surrounded by the sodium ions, and so on. They are arranged in this way to maximize the electrical attraction among them. There are many examples of ionic bonds. Some, like calcium carbonate, involve more than two elements. Ionic compounds share a number of similar properties. They have high melting points and tend to be brittle. Most dissolve in water, which separates the ions and makes the water a good conductor of electricity. Ionic bonds occur when electrons are transferred between atoms, but there are many substances formed when electrons are shared between atoms in covalent bonds in structures called molecules. A vast number of substances have molecular structures, including plastic, paper, all plant life, water, most of the air we breathe, and every tissue in the bodies of animals, such as humans. Molecules can be made up of as few as 2 atoms or hundreds of them. The DNA molecules that provide the hereditary code in every cell of our bodies are made up of about 1 billion atoms. It is the ability of atoms to join together into covalent bonds that result in the millions of substances that we find in the world. To describe the composition of molecules, chemists use molecular formulas, which precisely describe how many atoms there are in a single molecule. O2, for example, is a molecule of oxygen, which is in the air we breathe and flows through our bloodstream. O is the symbol for oxygen, and 2 indicates that there are 2 oxygen atoms in the molecule. This is the molecular formula for ordinary table sugar. It is a complicated molecule, but it is possible to see its composition at a glance. The molecule is made up of 12 carbon atoms, 22 hydrogen atoms, and 11 oxygen atoms. Molecules always arrange themselves in the same proportions because the atoms bond together in a predictable way. The chemical formula of a substance reflects these proportions. This is called the law of constant composition, which states a given compound always contains the same elements in the same proportion by mass. Pure water, H2O, for example, is always 88.9% oxygen and 11.1% hydrogen by mass. The principle that influences covalent bonding is the octet rule, the same rule that influences ionic bonds. In a molecule of water, H2O, the oxygen atom has 8 electrons, 6 of which are in its valence energy level. As this Lewis dot drawing shows, when the oxygen joins with hydrogen, the 2 electrons from the hydrogen atoms complete the valence energy level of the oxygen atom and satisfy the octet rule. The molecule also completes the valence energy level of the hydrogen atoms. Although the octet rule predicts the structural formulas for millions of molecules, there are many exceptions. Some atoms, particularly those elements that are beyond the second row in the periodic table, often form bonds that have an irregular number of electrons in the valence energy level. This is true of phosphorus and sulfur. Molecules have different shapes and sizes. Some have a linear shape. The centers of the atoms fall in a straight line. Others have a triangular shape. And still others have the shape of tetrahedrons. The reason atoms arrange themselves in this way is because of the attraction and repulsion of the electrical charges between the atoms. The length of the bonds varies, and many molecules have slight negative and positive charges. This is called polarity and results from unequal distribution of the electrical charges. When we crack an egg into a hot pan, it changes from a semi-liquid runny goop into a fried egg, ready to eat. The egg can't be uncooked and put back into the eggshell. It has undergone a chemical reaction. A chemical reaction is a process in which one or more substances are converted into new substances with different physical and chemical properties. During a chemical reaction, atoms can form molecules. Molecules can break apart or react with other molecules, and new bonds are formed. Some substances readily go through chemical reactions, but others do not, because of the arrangement of the electrons in the atoms and molecules. There are an incredible number of chemical reactions going on around us all of the time. All life processes, respiration, digestion, and reproduction, are chemical reactions, as are the combustion of gasoline in car engines, the rusting of metal, and the decomposing of plants. Chemists categorize reactions to describe what is happening at a molecular level. A synthesis is a union of substances into a new molecular structure, in this case, a polymer. A single replacement reaction is one in which one element displaces another. Here, we see sodium displacing hydrogen from water. And a double replacement reaction is an exchange of elements to form new compounds. Potassium leaves iodine behind and bonds with nitrate, and lead breaks its connection to nitrate and bonds with iodine. The rate of these reactions can be affected by temperature and the presence of a catalyst. Chemical equations are written to describe what happens in a chemical reaction. This is magnesium, quite a reactive element. When it reacts with hydrochloric acid, hydrogen gas is produced. It can be written magnesium plus hydrochloric acid produces magnesium chloride plus hydrogen gas. The arrow means yields or produces. The key to understanding chemical equations is that they must balance. Matter can never be created or destroyed. There must be the same number of atoms on each side of the equation. Is this chemical reaction written correctly? No. On the right-hand side of the equation, there is one magnesium atom, two chlorine atoms, and two hydrogen atoms. The equation does not balance. In order to make both sides of the equation balance, there must be two molecules of hydrochloric acid. This is now the proper equation. The system that chemists have developed for writing the equations for chemical reactions and the formulas for compounds are precise ways of describing the structure and reactions of elements at an atomic level. One special type of chemical reaction is called oxidation-reduction, or redox reaction. Oxidation refers to the loss of electrons, while reduction refers to the gain of electrons. Oxidation-reduction reactions occur when electrons are transferred from the atom that is oxidized to the atom that is reduced. There are a wide variety of redox reactions that occur in nature, from the rusting of iron, to breathing in animals, to the functioning of muscles. An important class of oxidation-reduction reactions are used to provide electric current in voltaic cell batteries. This is a simplified drawing of a voltaic cell battery. These types of batteries can be created using any two different metals, since metals differ in their tendency to lose electrons. We take advantage of this by connecting two such metals with a wire to allow electrons to flow from one to the other. This is electric current. In this example, zinc is placed in a zinc salt solution, zinc sulfate, and copper is in a copper salt solution, copper sulfate. Oxidation takes place at the electrode we call the anode, and reduction occurs at the cathode. Zinc atoms of the anode are oxidized, providing two electrons which flow through the external wire from the anode to the cathode. This causes the electric current to light the bulb. In their oxidation, the zinc atoms have become positive ions because they have given up electrons and they go into the solution. On the copper side, when the two electrons are received, they reduce a copper ion in the copper sulfate solution into a neutral copper atom, which attaches itself to the cathode. As this process continues, an imbalance of charge is very quickly built up in the battery, as positive charges are generated on the left and negative charges accumulate on the right. For the voltaic cell to continue to produce an external electric current and power the light bulb, there must be a movement of sulfate ions in solution from the right to the left to balance the electron flow in the external circuit wire. This is an oxidation-reduction process. At the anode, oxidation, or loss of electrons, occurs, and at the cathode, reduction, or gain of electrons, occurs. When scientists came to understand how elements bonded to become compounds, they were able to explain one of the great riddles that has puzzled us since the beginning of human civilization. What is the makeup of matter? There are only 92 elements that are found naturally in the universe. True or false? The process when atoms are broken apart to release energy is called fusion. True or false? When there is a change in the chemical composition of a substance, it is called a chemical. When an atom loses or gains one or more electrons, it becomes an. The octet rule states that atoms tend to gain, lose, or share electrons in order to acquire a full set of valence electrons. True or false? When electrons are shared between atoms in covalent bonds, they are called. Molecules never arrange themselves in the same way. True or false? A chemical reaction is a process in which one or more substances are converted into new substances with different physical and chemical properties. True or false? Chemical equations do not need to balance. There can be different numbers of atoms on each side of the equation. True or false? The electric power in a battery is generated by a chemical reaction. True or false?